All right, so today we're going to talk about this thing called optimization, okay? But before we do, I just want to remind us about what calculus is about, because it's easy at this stage in the semester to forget what the whole point of everything was, right? So remember, calculus addresses two questions. The first is you know how much of something there is, and you want to know how fast it's changing. And the other question is you know how fast something is changing, and you want to know how much of it there is, okay? So my question to you is, with all of this stuff that we've been working on with the mastery test, which of those two questions have we been answering? Yeah. Which one of these scenarios are we looking at from the mastery test with all of those rules? The first one, right? So we were finding closed form derivatives, right? Which is another way of saying finding a rate of change function for a given function, right? And then even once we've moved on to this related rates type of problems to work on, right? Once again, how do we solve them? We have to identify quantities involved in the problem and how they're related to set up a formula relating those quantities to then take a derivative to find the rate of change of those quantities, okay? So we've been addressing this first question, okay? So we've been doing what's called differential calculus. Before the semester is over, we will visit integral calculus, but we're not quite there yet. But we're sort of like tapping our toes on it a little bit, okay? So, so let's take a look at some questions. So we're finally going to start thinking again, okay? So sorry, I shouldn't say it like that. You've probably been thinking. I hope you've been thinking at least. So let f be any function, all right? If the rate of change of f is positive, then what can we say about f itself? I heard a mumble. Scott? F is increasing. I agree. How do you know? Arian? So the rate of change is positive. Okay, yeah, that's what that says. So if the rate of change is positive, then f is increasing. But how do you actually draw that conclusion? Yeah, Ahmed? Beautiful, right? So remember, the meaning of the derivative is that for little change, so if it's positive, it means that if I change a little bit in x, then the corresponding change in the output value, the accumulation value, is going to change by some positive value times as much as the change in x, right? So that's going to cause an increase, right, in the value of f, okay? So then so we're just going to sort of like hash this in, okay? So let f be an accumulation function, okay? So the difference, of course, is that before I just said let f be any function. Now I want to specifically think about an accumulation function. What does it mean for the graph of f if the accumulation is increasing? What does it mean to say that the graph is increasing? Somebody else. The quantity is increasing? What does that look like? Yeah. The y-axis is going up? The y-axis is just the y-axis. It's not going anywhere. The y-values are going up as what happens? As x increases. So from left to right, the y-values are getting bigger, right? Okay. All right. So then if f is a rate of change function, r sub f is the rate of change function for the accumulation function f, right? So then what does it mean for the graph of f that r sub f is increasing? So this one's a little bit trickier. Okay, so what does it mean for the graph of f to say that the rate of change of f is increasing? So it today is going to be a 4-letter word. We're not going to say it, right? So what's increasing? So the output of f of x is increasing. Okay, Kyle's got something to say. F of x is increasing at an increasing rate. Yeah? Ooh, I like the way you said that. Yeah. So for equal changes in x, the corresponding changes in output of f are getting bigger, right? Yeah, that was really nicely said. We have a name for that. It's called concave up. Okay. So I'll write it down. But really, what I should be writing down is that beautiful phrase. So for equal changes in x, the corresponding changes in output are getting bigger, right? That's nice. I like that a lot. Okay, so then here's the thing, though. I've heard a lot of people saying things about f is increasing. So notice that this doesn't actually say that. That's not what this says. Okay, it just says that the changes in f are getting bigger, right? So what I want you to be careful of is thinking, so saying that the rate of change is increasing does not necessarily say that f is increasing. Can you think of a reason why? Scott? Good, right. So saying that the rate of change of f is increasing does not mean the rate of change of f is positive, right? Which is what you need, right? So that's what we were talking about up here. You need the rate of change of f to be positive in order to say that f is increasing. But you can have a rate of change that's increasing and still be negative, right? So that would translate to having a decreasing function, right? But where but if those, so, okay. I'm going to get tongue-tied. Actually, I guess I could just go like this. So the thing that we could be visualizing, right? So if the rate of change is negative, but it's increasing, then that means that the negative values are getting less negative, right? So smaller decreases. Blah. It's a lot to coordinate, right? Okay. All right, let's keep going because it'll be easier when we actually see pictures. Okay, so let f be any function, once again. So now if I say that the rate of change is negative, then what can I say about the function itself? Oh, that's what I just said. What does that mean? If the rate of change is negative, then f is decreasing. And again, how do you know? How would you explain that? Exactly. So for a given change in x, the corresponding change in output value is going to be a negative amount times that change in x. Okay, so that's going to correspond to a decrease in the output value. Okay. So once again, we can ask a lot of the same questions. So now if I'm talking about an accumulation function, What does it mean for the graph of f if the accumulation is decreasing? What does that look like? Ahmed? Oh, careful. So I'm just asking, what does it mean for the graph of f if the accumulation is decreasing? Jonathan? Any ideas? Not at the moment. Shelly? Any ideas? No? Taylor? Other Taylor? You.
Given the same changes of x, the same equal changes in x, the changes in y are going to be smaller.
Okay. So let's reread this sentence. Let f be an accumulation function, f of x. What does it mean for the graph of f of x if the accumulation is decreasing? The only word that's referencing change here is decreasing. So I'm not asking about, I'm not telling you something, like I'm not asking about the rate of change function. I'm not talking about the rate of change with the rate of change. I'm not talking about any of those things. I'm just asking, what does it mean for a graph to be decreasing? What does that look like? Jan, right? Yep. Ah, you're still telling me about advanced things. This is a basic question. When I say a graph is decreasing, what are you visualizing? The y values are doing what? They're going down, right? As you move left to right on the graph. That's all I was asking for, okay? So, but what we just saw, this whole conversation, is exactly why I'm having it, right? So I just asked you a simple question. We have introduced a lot of calculus. And when I introduce lots of calculus, people forget the things that they already knew, right? And they get jumbled, okay? So I'm drawing your attention to this because where we're going today is really confusing if you're not careful about paying attention to whether or not you're talking about an accumulation function or a rate of change function, the difference between positive and negative versus increasing and decreasing. All of these things I know you know individually. I'm about to start asking you questions about all of them simultaneously, and it gets sticky, okay? So you have to read the questions carefully, and you have to pay close attention to which of those things we're talking about, okay? So then let's try again. Let's ask this question. So now I'm going to talk about the rate of change function of f. What does it mean to say that the rate of change function is decreasing? Okay, so now I'm not talking about the function f, the accumulation function f decreasing. Now I'm talking about the rate of change function of f decreasing. Harrison? Okay, so you just said if the function itself, if f is decreasing, and the rate of change of f is also decreasing, then it's concave up. Okay. So I would like an answer that doesn't depend on whether or not f itself is increasing or decreasing. Okay. Yes. Okay. So the corresponding changes in y value will get smaller and smaller. Okay. So all right. I'm feeling like pictures are going to be helpful. Let's look at some pictures. So we're going to work before we go straight to the helpful part, okay? which is once again, so here, can everybody see? Do I need to try to make it bigger? I don't know if I can actually. I forget. Documents, settings. There we go. Okay, so so what I've got here is a function, so ignore the view stuff, that's for me. Okay, so r of x equals the rate of change of f of x. So what's the implication for what kind of function f of x is? F of x is a rate of change function? Chances are it's an accumulation function, right? Because I'm taking its rate of change, right? So that's not to say that it couldn't be a rate of change function, though. And that's actually where we are going today. We're going to eventually talk about rate of change functions, right? But for now, let's imagine that it's an accumulation function. And so r of x is its rate of change function, okay? So what I've got here is n is a slider so that I can talk about different values of x, and r of n outputs the corresponding rate of change at that x value. Okay, so notice that this value, this r of n value, is not the value of f. It's the value of r. Okay, so it's outputting what type of thing? An accumulation or a rate of change? A rate of change. Okay, so in particular, let's think about what does it mean for the moment. If I were to graph this ordered pair, what would be the meaning of that ordered pair? 4, -4, 34. What's the meaning of that ordered pair? Yes. Okay, so at x equals -4, the rate of change of what? Okay, so the rate of change of the function f is 34, which means that near x equals -4, small changes in x will result in a change in y 34 times as large, right? Okay, so now I'm going to move my slider so that x ranges, or n ranges between -4 and -2.5. And I want you to pay attention to what happens to the rate of change value. Okay, so I'm going to move it. So what's happening to the rate of change? I'll do it again. Whoa, too far. So from -4 to -2.5-ish, what did the rate do? It decreased, okay? So the whole time, though, it was positive. So if I wanted to record some things about what was going on, what could I record? So between -4 and -2.5, what could I say? I could say that the rate function is positive, right? But decreasing. What does that mean about the function f? What does it mean to say that the rate is positive for f? Yeah. Okay, so f is increasing. So visually, that means it's going up, right? But the fact that the rate itself is decreasing while remaining positive the whole time means that as f is increasing, it's increasing in smaller bits, right? Okay. But at a slower rate. Okay. So can you visualize or sort of like draw it with your finger what would that look like if you were to graph it? So I'm seeing, give me what you got? Okay, over here, I didn't see what you got. Okay. Huh? Okay, so you guys know fancy words. Let's not worry about the fancy words. But yeah, okay. So that would look something generally like increasing, but at a slower and slower rate, right? Okay. So then if we take a look now between negative 2.5 and negative 1. Once again, I want you to pay attention to what happens to the rate. Okay, so between negative 2.5 and negative 1, what happens to the rate? Okay, I'm going to do it again. So from negative 2.5, I'm going to make it go smooth now. Okay, so negative 2.5. Whoop. I really can't do this whole click button thing. Okay, what happened? So what can you say? So R of X starts out positive, right? But what does it do? It becomes negative. So R of X changes from positive to negative, right? So one thing that I could have said more easily is that it continues to decrease, right? It's decreasing the whole time. Did it ever start to go back up in this interval? No. Okay. So, so it changes from positive to negative. So the implication there is always decreasing. Okay. What does that mean for our function f, our accumulation function? So while the rate of change is positive, what is f doing? It's still increasing, right? But then as soon as the rate changes to negative, it starts to do what? Starts to decrease. So at some point in time, if you will, or at some x value between negative 2.5 and negative 1, my rate has to go through 0, right, in order to go from positive to negative. And so, right, so we can imagine what that would look like. So it goes from increasing to decreasing at the corresponding x values where the rate changes from positive to negative. So once again, what would that look like? Give me a, what's it do? I've already forgotten. Name? Mm-hmm. Courtney. What do you think? Okay, so it's going up and then down, right? Okay, so something like, so it still has to increase for a while. Oops. So it's still increasing, but then it starts to decrease. Okay. Okay, and then if we keep going, so between negative 1 and 1/2. Okay, so what does the rate do? What did it do? Is it better when I try to make it play smooth? Let's see. So what did the rate do? One more time. Was it increasing the whole time? Mm-hmm. So R of X is negative the whole time, but it decreases for a little while, a little bit. Then it switches to increasing, right? But the whole time it's negative. So what does that mean about the function f? It's decreasing the whole time because the rate of change is negative, but the rate at which it's decreasing, the rate at which it decreases, increases for a little bit and then decreases, right? So visualizing, what am I going to draw? What am I going to draw? Was it no, Bethany. Where's Bethany? Bethany wasn't here. Harrison, what's the girl's name next to you? Miranda. Great. Miranda, what do you think? You don't know? If the rate is negative, what is the function doing? Mm-hmm. Dakota, can you help her out? It'll be decreasing, okay? And so decreasing with a bigger negative, right? Before that negative starts to increase again. So it'll be steeper for a while, right? Steeper for a while, and then like be not as negative. Make sense? I probably shouldn't have flattened it out like that. It shouldn't be flat. It should still be decreasing, but just not as much, right? Okay. So we could keep doing this, right? But here's something that I haven't taken into account yet, which is that what I've done here is drawn a general shape for what f could look like. Is this definitely the graph of f, though? What information have I completely ignored? The actual values of f, right? So this curve is a curve of the behavior of what f will do, right? It's going to increase at a decreasing rate, and then it's going to decrease at an increasing rate for a little while, and then it'll start. You know. So we've sketched what it will look like generally, but it's not until I actually fix a value of f where you could like start drawing and then start drawing out this curve where you would actually get the graph of f. Okay, but let's just at least check our work a little bit. Okay, well, I'll take the blame for this one. But you can kind of see that it still looks kind of like it, right? So like increasing and then decreasing. So, all right. Don't pick on me too much for my drawing. Okay, but what we can see is at least, right, that the shape of the curve follows sort of what I've sketched, okay? Now, so let's just make sure that we understand what we're looking at in this picture. Okay, so help me figure it out. So I've got this picture where there's two graphs, right? The red graph and the blue graph. What is the blue graph representing? The blue graph is representing the rate of change at the given x value, right? So that's almost beautiful. We're getting closer. Okay, so I agree that the blue graph is related to the rate of change at that point. Is the whole graph the rate of change? So the slope of the blue graph is the rate of change at the x value where it meets the graph of f of x, right? There's a lot going on there. So what I'm just trying to convey is that this blue graph is not just saying it's the rate of change doesn't actually make sense, right? Because this blue graph is a collection of points, right? There's infinitely many points in that graph making up that line. Every one of those points is not the rate of change, right? It doesn't make sense to say that a collection of points is the rate of change. That's a nonsensical sentence, right? But the slope, if you will, of this graph gives you the rate of change at the x value where it meets the graph of what? What is the red graph? This is the graph of f of x. So this is our accumulation function, okay? How are we feeling? So can you see, can you see how as I let x change, we can think about sort of how so if you concentrate, so what I want you to concentrate on is the slope of the blue graph, right, as we move. So the slope is like really big positive and then decreasing positive until at one point it actually gets to be 0. and then it starts to be negative, but it's like a little bit negative, and then really negative, right? And then less negative, and then back to 0, and then a little bit positive. So you can see how you can kind of trace it out, right? And so while we're tracing it out, the things that we can connect these back to are the derivative, but also the rate of change of the derivative, okay? So that's what I want to talk about a little bit. So where'd it go? Okay, so I've got the same, it's the same image, the same graph, but I've got some questions for you. Okay, so where is the accumulation of F decreasing, and how can you tell in 2 different ways? Yes, the red graph is the accumulation graph. And the blue graph is still the graph of the rate of change at a given point, all that stuff. Okay. So where is the accumulation F decreasing, and how can you tell? You can talk to each other. Sure. All right, what you got? Yeah. Okay, anywhere the rate of change function is negative, F is decreasing. Do you buy it? Okay. That's like the calculus way to tell. What's the other way? Yeah. Yeah. When the actual value, the output of the function, right, the y values of the red function are getting smaller. That's the other way to tell, right? So 2 ways to tell. You can actually look at the values getting smaller, or you can look at the corresponding rate of change values being negative, right? So those are the 2 ways to tell. I think I typed that in already. So if the rate of change of F is negative, then the accumulation is decreasing. Okay? I only wrote down the calculus way, because the other way, I feel like you guys got that, right? Or should I type it down? You want the other way too? Okay. All right, so where is the rate of change of F decreasing is my next question. And once again, I sort of want you to kind of think about what that would mean. So where is the rate of change of F decreasing? Oh, did you actually tell me where the function was decreasing? The accumulation function? Like an approximate interval? So from about here, so like negative 1.9-ish to about here, right? About 1.2. Okay. where is the rate of change of f decreasing? So where is the rate of change of f decreasing? All right, are we ready? Do you guys have an approximate interval that you can tell me? From where to where? -4 to about 1. So I heard +1, I heard -1.9. Oh, I'm getting all kinds of fun answers. All right, so I agree that we can start with -4. Let's figure out how we would keep going, okay? So over where the graph is showing right now, what kind of slope am I looking at, or value of rate of, so i.e. the value of the rate of change am I looking at? It's positive and it's big positive, right? I could like approximate what that slope is and it would be a big number, okay? A big positive number. Now as I move, what's happening to that big positive number? It's getting smaller, so it's decreasing. So the value of the rate of change is decreasing, right? Because we're getting smaller positive. And then we get to a point where it's 0, so we're still decreasing, right? And then it starts to be negative, right? What kind of negative is this? It's kind of like a small negative, right? But then it gets to be bigger and bigger negative. So are we increasing or decreasing? We're still decreasing. Still decreasing, still decreasing. But then starting around here-ish, something changes, right? The slope starts getting less negative. So when it switches from getting more and more negative to being less and less negative, that's when the rate of change switches from decreasing to increasing, okay? So I would say, where did that happen? Whereabouts? Okay. I'm just going to be stubborn and say -0.3. Okay. Ish. Okay. So what does this mean again, though? So the way that we worked our way through that is the rate of change is becoming less positive or more negative. Okay. So once again, that trickiness with negatives and increasing and decreasing, it takes some focus. Okay. So that was the point of this exercise. There's one more question, I think. So if the rate is decreasing, what can you say about the rate of change of R of x? So I'm saying R is decreasing. What can you say about the rate of change of R? People just came to that conclusion in an instant. Maxwell, how did you come to it? Yes, right? So if you were to sort of reframe your brain and say, well, instead of thinking about R as the rate function, let me think about it as if it were an accumulation function. So I've got a function that's an accumulation function that's decreasing. How does that relate to its rate of change? Well, that means its rate of change is negative. Okay. Yeah? Okay. Now warp your brain a little bit again. Okay. So in order to think about part B, R can't be the accumulation function anymore, right? R really does have to be the rate of change function. So the rate of change function is decreasing. What can you say about the graph of the accumulation function f? So let me remind you that we just said that the rate of change was decreasing from -4 to about -0.3. So what is the graph doing from there to there? It's not decreasing, right? So you can't say that the graph of f is decreasing. But you can say what? So I agree that that's what it's doing between that's what the graph is doing between -4 and -2. But remember, the rate is still decreasing from -2 to -0.5, and the graph is not increasing there, right? It's decreasing. The changes in output of f are right? So the changes in the output are big here, right? They're big positive, and then they're smaller positive, and then they're smaller positive, and then they're smaller positive, and then they're basically zero, and then they're negative, and then they're more negative, and then they're getting smaller, right? A bigger negative is a smaller number. Negatives are tricky. Okay? A bigger negative is a smaller number. Okay? All right, so we have a name for this. It is concave down, okay? Like a friend. Okay. But I don't want you to just memorize that word, right? That phrase, concave down, in and of itself is meaningless, okay? What does it mean? It means that the changes in the output of f are getting smaller, okay? So let me at least get up on the screen for your notes a couple of things, okay? So what we just talked about, the saying that the rate of change is decreasing, we were talking about the rate of change of the rate of change. So when we say that, we're talking about what's called a second derivative, okay? So the rate of change, the rate of change of the rate of change with respect to x is the derivative of the rate of change of x, right? Or the derivative of the derivative, the second derivative, okay? So notational devices that you'll see for this, you won't really see the first one all that often, but the next three you will see in practically any textbook you look at, okay? You could imagine continuing this process and taking the third derivative, the fourth derivative, the fifth derivative, etc., right? It's an iterative process where you have to take one derivative and then clean it up and then take the next derivative, clean it up, do it again, right? But for now, we're only going to concentrate on the first two derivatives because we can make meanings of those graphically, okay? So once again, let me just just give me like 2 more minutes of your time. Okay, so we say a graph is concave up if the rate of change of f is increasing. We say f is concave down if its rate of change is decreasing. And we identify these special points on a graph called inflection points where the concavity changes. So if the graph changes from being concave up to concave down, the point at which that change occurs is called an inflection point. And likewise, if it changes from being concave down to concave up. Okay, so that would look something like, ooh, I don't know what I just pressed. Oh. Sorry. So that would look like, so concave up looks like this. Concave down generally looks like this. So an inflection point would be something like, so concave down here, and then somewhere around this point it switches to being concave up, or vice versa. Okay, so these points that I'm highlighting would be referred to as inflection points, okay, because the graph changes its concavity. Notice that do lines have concavity? The rate of change of a linear function is what? The rate of change of a linear function is a constant. So its rate of change can neither increase nor decrease because it's constant. So we can't really talk about the concavity of a linear function. Okay, so expect to be seeing more interesting functions on your homework. Okay. All right, I'm gonna have to stop there for now. Your homework in the video is going to be posted a little bit later than usual today, as well as the quiz information for next week because I have to give this talk. But as soon as I'm done with the talk, then I'll be able to put everything together and on Blackboard. Okay.